Excellent. Good. Thank you very much for hanging on. I'm here to tell you about, well, the title of the talk is A Quantum Leap for York. And I guess this all started in terms of the quantum leap for York towards the end of 2013. So I was quite busy around then, and a number of things were happening. And the two really important things with respect to this quantum leap were, firstly, I agreed to move to the University of York to set up the new York Centre for Quantum Technologies. And although I'm based in physics, I want to stress immediately that quantum technologies, and I'll come to what those are partway through the talk, quantum technologies don't just include physics now. They may be based on quantum physics, but they embrace other academic subjects, and so the York Centre includes people in mathematics, people in computer science, and I hope in the future people in other departments as well. So it's a broad interdisciplinary activity, quantum technologies. So around the end of 2013, I agreed to move to York to set that up. And the other thing that happened around then was this. So the then Chancellor of the coalition government, George Osborne, found £270 million of new money, or essentially new money anyway. It wasn't stolen from the basic research budget, but he was persuaded, a number of us have been lobbying for quite a while, to produce a large amount of money that could be invested in this new area. So after the Nobel Prize in Graphene, there was 150 million or so found in this. This is a very big investment, £270 million in one area. And so the moment that was announced, of course, we then all had to start aligning ourselves within the UK and deciding how we could bid for and spend this money. And what that money got devoted to in the end, the centrepiece of it, if you like, are 4 quantum technology hubs. These are each big collaborations. They include many universities and, very importantly, industrial companies. And so I pulled together one collaboration we bid, and I am now leading one of these 4 hubs that form the centrepiece of this quantum technology program in the UK. So it includes 7 other universities and many companies. And I'll come to what we're trying to do in that hub in just a bit, but I should point out there are other things. The Centres for Doctoral Training in our area got boosted. There's a new metrology centre at the National Physical Laboratory in Teddington in London. There are new training and skills hubs that are about to be announced, and there's new capital money as well. So there's a big programme now put in place to invest in quantum technologies in the UK, which, if you like, was stimulated by other countries doing similar investments, but this is a big one for the UK. So I think on the world stage now, people are listening to us because we are really playing in this space worldwide with this investment. So if you look at what Philip Nelson, who is now head of the EPSRC, says, then he points out that these hubs will build on the previous investments on quantum science. So I stress that this money is new. It's not stealing from the conventional science budget. And in fact, the conventional quantum area within EPSRC is still being heavily invested in. It's a growth area still. And so it's quite interesting. If you've ever had money from EPSRC or a funding council, these quantum hubs are completely unlike that. They are focused on technology development, so they are focused on building what the basic research has developed over a number of years in terms of the science base. They are actually taking that science base and turning it into working technology. So that is our objective, that we're supposed to take what we've already been doing for the last 20 odd years in quantum physics and turn that now into working technology. Before I move on, there's a couple of other points I'd like to make. Philip Nelson has fairly recently taken on being head of EPSRC. The former head, his predecessor, David Delpy, is actually now in charge of the UK National Quantum Technology Programme. So he has transitioned from being head of EPSRC into leading this programme in the UK, which I think gives you a sense of the importance that at least he feels that this programme has. So it's a big investment, and we've got to deliver in order to justify it. So Dave Delpy has moved on to that. Now let me get to quantum technologies. So when I went to university to learn about quantum physics, and I hesitate to admit that's nearly 40 odd years ago now, I learned about all the interesting fundamental aspects of quantum physics. And of course, from the fundamental perspective, they are fascinating and really interesting. But it was hard to see at that time how any of that would have any impact on daily life, stuff that you do every day. It was interesting science, but it wasn't clear what application it might have. That has all changed. So through my career, I have seen ideas develop where we now know that the fundamental and interesting features of quantum physics, the most interesting bits, can play center stage in new technologies. And that's what this field of quantum technologies is all about. And what I'd like to do, I'm assuming that most of you are neither familiar with quantum physics nor quantum technologies. So I have 3 slides which are your crash course in all the interesting bits of quantum physics that we need and what those capabilities are. So the idea is that if you can build a new technology incorporating some piece of quantum physics, you will be able to either do something that you haven't been able to do before, or you will be able to do rather better than you can do with conventional information technology. So these new quantum technologies are pushing the boundaries beyond where we can currently go with ordinary information technology. So as I say, you've now got 3-slide crash course on quantum physics. So here's the first one. One of the interesting features of quantum physics is that quantum things can be in more than one state at the same time. They can do multiple things at the same time. So if you think in terms of computing, when you compute things, if you want to do parallel processing, you need a separate processor for each of the parallel paths that you are doing your parallel processing in. If you have a processor that can work according to the laws of quantum physics, you can do all those parallel paths within the same device. You can shove all of those parallel paths of computation into a single quantum device. And interestingly, the number of paths that you can have here grows exponentially with the quantum resources that you have. So the number of parallel paths that you can compute with grows incredibly rapidly with the resources that you have. And that doesn't mean that every single computer will be improved for every computation in the future, but we know already that there are many computations that you might want to do where you can get an enormous speed up if you can do that computation within a quantum machine. Now, the quantum computing technologies are still really in their infancy. One of the 4 hubs that has been funded, led by the University of Oxford, is actually pushing in this area. They're going to try and build a quantum computer by putting little ions in a trap. At the minute, they've only got a few of them, so they're not going to be doing huge computations, I think, in the next few years. But nevertheless, they're going to push quantum computing technology in that direction. So that's the first quantum technology that's of interest, quantum computing. The next one is using this weird and wonderful quantum effect of entanglement. And so another feature, as well as being in multiple places or states at the same time, quantum things can also, when they are separated, have correlations between them that are stronger than any correlations you can imagine or you will have ever seen in the everyday world. They can be more intimately linked. They can be more strongly linked together. That is called entanglement. That's the fancy word for it. And if you have quantum stuff that you put in an entangled state, then if you do something like this in this rather simple diagram, if you bounce some of it off an object that you're interested in imaging or sensing or measuring, and you keep the other bit of it, and then you compare the two after this one's bounced off the object, then you can learn about that object. You can image it, or you can measure it in some way, or you can sense that it's there more accurately than you can do with any conventional sensors. So it gives more accurate measurement and sensing. Now, there are 2 of the hubs, so I'm getting to mine in just a minute, but 2 of the other hubs, one led by the University of Glasgow, one led by the University of Birmingham, are focusing on this idea that quantum entanglement and other quantum effects can enable better and more accurate sensing and measurement. And so 2 of the hubs are devoted to that, which leaves the final one, the one that I coordinate, and that is focused on the last quantum effect I want to talk about, and that's quantum communication technologies. And the fundamental feature of quantum physics that underpins quantum communication technologies is, well, I've called it quantum uncertainty on the slide, but if you come along and try to measure something quantum, then you disturb it. And that's not just because we're big and clumsy and we're going to get better at doing it in the future. That disturbance is fundamental. It's built into nature. It will not go away. It's a limitation that is built into nature. And so because of that, you can use that to underpin the idea of secure communications. Now, in secure communications, the two people are always called Alice and Bob. So I don't know what you do if you're not called Alice or Bob. But anyway, we always think about Alice talking to Bob in communication scenarios. And the idea is that if Alice sends something quantum to Bob, if there is someone in the middle who is trying to eavesdrop and learn about what Alice is sending to Bob, the only way she can do that is to try and measure what is being sent. If she measures it, she will disturb it and therefore be detected. And so an eavesdropper will always be detected when you're sending quantum stuff from one place to another and the eavesdropper is acting in the middle. And so that can be used as the basis of secure quantum communications. I'll say a little more about that now because that's the focus of the hub that I lead here from the University of York, which is the fourth of these in the great big UK program. And so if we look at quantum communication technologies in a little more depth, the idea is that because of this fundamental disturbance that exists when you measure things, you have a promise from nature that any eavesdropping will be detectable. And so if you like, you have a promise from quantum physics which underpins the security of your communications. Now, Alice and Bob are quite clever because what you would perhaps naively think of doing is actually trying to send a message encoded in your quantum signals. Well, you don't do that because obviously if someone does intercept them, they can at least deny service, they can destroy your message or whatever. So what Alice and Bob do is rather than send the message, they use the quantum signals to establish a key. They want to share a key between themselves with a promise that that key has not been compromised. No one knows any information about it other than themselves. And so that's what they do. And currently the most sophisticated quantum communication systems are based on doing this. So the fancy word for it, or the acronym for it, is QKD, quantum key distribution. Alice and Bob send quantum things between each other. They measure them themselves. And there's a clever protocol whereby they can then establish a key. So they both have a list of numbers. And they have a promise from nature that nobody else knows anything about those numbers. And then they can use those keys for a number of things. They might want to encrypt a message, but there are other applications as well. But the key thing I want to stress is that the quantum part of this is the establishment of the key. And because the key is a consumable, you're only supposed to use it once, then you delete it. You're not supposed to reuse it, otherwise you get into trouble, just like various crypto systems have been broken in the past. You should not reuse keys. But keys are disposable things, you use them once. That means you need to replenish them. So when you establish them or when you replenish them, you do quantum exchange of stuff. Once you have the key shared, you can use these numbers, because they're ordinary numbers then that you've got stored, you can use them for whatever you want. And there's a whole range of applications which may well involve communication, but it'll involve other things as well. So what we're trying to do in this quantum communications hub is that we're trying to take, I mean, I'm old enough to remember when mobile phones didn't exist at all and we just had landlines. Then you got great big things like this and you now know what fancy mobile phones look like today. Well, we want to take quantum communications through a kind of transition in the same way that conventional communications has been through a big transition in the last 30 years. And so what we're aiming to do is to utilize quantum keys and distribute them so that they can be employed in various ways. So, as I say, you might want to use them for just communication, but in principle, if you share keys with your bank or your employer or the government or whatever, you could use those keys for various things. You could use them for getting through the door or for passwords, a kind of disposable password that you recycle each time, or in the end, maybe for IDs or passwords. You could certainly use them to authenticate a transaction on the internet or something if you shared keys with Amazon or with your credit card company. And so there's a whole range of applications of keys, not just encoding messages and sending those messages. But what we're aiming to do, so this is the first of the three things that we're aiming to do. And I should stress that because, as I said, these hubs are about technology development and not about doing more basic science, we've got deliverables. We've said we will actually push some stuff far enough in the 5 years of the hub, and so we've had about a year already. We've got 4 left. we've said we will push stuff far enough that it would be in principle then commercializable, so it can be taken up, which is why we've got industrial partners involved working with us already in the hubs. They're not just waiting in the wings, they're actually working with us on this technology. So the first technology that we're going to try and get commercial ready, if you like, within the next 4 years, within the big collaboration in the hub, is short-range free space quantum communication. So you might imagine that some future version of the iPhone or whatever phone you prefer might have built into it a small quantum communication unit that will talk, so when you go and get some cash out of the wall or you go and fill it with petrol or something, you would also top up a quantum key with some device, and that might be topping it up with your bank or with credit card companies or whatever. But short-range free space quantum communication would have a wide range of applications for consumers, for people like us. And so that's somewhere where real quantum physics could actually have an impact in everyday life. We could all be carrying around a small quantum transmitter in the future that would enable us to establish quantum keys. That's one of the things we're aiming to achieve in the next few years. Another thing is, well, I've used, here's an illustration of a rather old computational machine. I'm sure your fridge now is far more powerful in terms of computation than this. The reason for that is Moore's law, and things have been getting smaller and smaller and more powerful all the time. That's true in electronic technology. It's now also going to become true in optical technology. So a lot of stuff at the moment with optics, and optics is used for high-speed communications, a lot of stuff with optics is quite bulky. But in the end, a lot of that will be reduced down to chips. And so our idea is that not only the Alice transmitter unit, but also, if you like, the Bob receiver unit will both be chip-scale things. So things that sit on a big optical rack at the minute. We want to get down to that sort of size. That's another thing that we're aiming to do. And then you could have Alice and Bob units in laptops, computers, and everything. And you can start to see quantum secure networking coming in a role there. The third thing that we've said we'll do in the hub is that we're going to build a kind of test quantum network within the UK. So there are various places in the world now where these are being built, and we're now going to build one in the UK. And it's going to be focused down in the south of England, I'm afraid, because that's where the national dark fibre infrastructure links exist that we're going to be building upon. But this is going to enable us to demonstrate what can be done with quantum communications. Very importantly, engage with potential end users at a business level, because at one of our hub partners, Bristol, will have a small network, and also in Cambridge, and we're now going to link to BT at Astral Park as well. And at each of these sites, there's quite a big range of potential customers or users. And so we want to build a quantum network and actually open it up to these people to have access to it so they can see what capabilities secure quantum communications have. So that's the third, if you like, big deliverable that we're going to do in the hub. So that's what we're aiming for in the hub. Eventually, we might want to go worldwide. So I'm not claiming we're going to be doing this, but I just want to whet your appetite with my final slide to show you what might be possible in the future. So I've talked about a connection within the UK, that would be down optical fibres, but in the end, you could potentially do secure communications worldwide. If you can get light up to a satellite and down again somewhere else, then in principle, you can link different countries or different continents together with secure quantum communications. That is not as daft as it sounds. The optical depth you need to get to a satellite is actually not so big, and people have already done long-distance quantum communication experiments on the surface of the Earth that will go through that kind of optical depth without a problem. So it's not actually getting through the atmosphere, it's actually pointing at the satellites that's going to be the problem. But there are now experiments that will be underway in the next few years, and these are going to be more worldwide collaborations, but there will be experiments underway in the next few years to do test communications at the quantum level between ground and satellite. So in the end, we could be thinking about a worldwide network for quantum communications. Thank you very much.